The Riemann zeta function or Euler Riemann zeta function, I paragraph, S, is a function of a complex variable S that analytically continues the sum of the infinite series, which converges when the real part of S is greater than a 1. More general representations of I paragraph, S, for all S are given below. The Riemann zeta function plays a pivotal role in analytic number theory and has applications in physics, probability theory, and applied statistics. This function, as a function of a real argument, was introduced and studied by Leonhard Euler in the first half of the 18th century without using complex analysis, which was not available at that time. Bernhard Riemann, in his article on the number of primes less than a given magnitude published in 1859, extended the Euler definition to a complex variable, proved its meromorphic continuation and functional equation, and established a relation between its zeros and the distribution of prime numbers. The values of the Riemann zeta function at even positive integers were computed by Euler. The first of them, I paragraph 2, provides a solution to the Basel problem. In 1979, APA copyright LY proved the irrationality of I paragraph 3. The values at negative integer points, also found by Euler, are rational numbers and play an important role in the theory of the modular forms. Many generalizations of the Riemann zeta function, such as Dirichlet series, Dirichlet L functions and L functions, are known. Definition: the Riemann zeta function I paragraph, S, is a function of a complex variable ZA equals AI florin A plus OIT. The following infinite series converges for all complex numbers S with real part greater than a 1, and defines I paragraph, S, in this case. It can also be defined by the integral. The Riemann zeta function is defined as the analytic continuation of the function defined for I florin A 1 by the sum of the preceding series. Leonhard Euler considered the above series in 1740 for positive integer values of S, and later Chebyshev extended the definition to real ZA A1. The above series is a prototypical Dirichlet series that converges absolutely to an analytic function for S such that I florin 1 and diverges for all other values of S. Riemann showed that the function defined by the series on the half-plane of convergence can be continued analytically to all complex values S A permel 1. For ZA equals A1, the series is the harmonic series which diverges to plus A, and thus the Riemann zeta function is a meromorphic function on the whole complex S-plane, which is holomorphic everywhere except for a simple pole at ZA equals A1 with residue 1. Specific values: for any positive even integer 2n, where b2n is a Bernoulli number. For negative integers, 1 has. For n a permel 1 yen, so in particular I paragraph vanishes at the negative even integers because bm equals 0 for all odd m other than a 1. For odd positive integers, no such simple expression is known. Via analytic continuation, one can show that gives a way to assign a finite result to the divergent series 1 plus 2 plus 3 plus 4 plus AAA, which can be useful in certain contexts such as string theory. This is employed in calculating of kinetic boundary layer problems of linear kinetic equations. If we approach from numbers larger than 1, then this is the harmonic series. But its principal value exists, which is the Euler-Mascaroni constant. This is employed in calculating the critical temperature for a Boussy-Euro-Einstein condensate in a box with periodic boundary conditions, and for spin wave physics in magnetic systems. The demonstration of this equality is known as the Basel problem. The reciprocal of this sum answers the question, what is the probability that two numbers selected at random are relatively prime? A. This is called APA copyright Y's constant. A. This appears when integrating Planck's law to derive the Stefani-Boltzmann law in physics. Euler product formula: the connection between the zeta function and prime numbers was discovered by Euler, who proved the identity. Where, by definition, the left-hand side is I paragraph, S, and the infinite product on the right-hand side extends over all prime numbers P. Both sides of the Euler product formula converge for E, S, 1. The proof of Euler's identity uses only the formula for the geometric series and the fundamental theorem of arithmetic. Since the harmonic series, obtained when ZA equals A1, diverges, Euler's formula implies that there are infinitely many primes. The Euler product formula can be used to calculate the asymptotic probability that S randomly selected integers are setwise K'. Intuitively, the probability that any single number is divisible by a prime, p is 1/p. Hence the probability that S numbers are all divisible by this prime is 1 per picosecond, and the probability that at least one of them is not is 1 per picosecond. Now, for distinct primes, these divisibility events are mutually independent because the candidate divisors are K'. Thus the asymptotic probability that S numbers are K' is given by a product over all primes. More work is required to derive this result formally. The functional equation, the Riemann zeta function, satisfies the functional equation, where I, S, is the gamma function, which is an equality of meromorphic functions valid on the whole complex plane. This equation relates values of the Riemann zeta function at the points S and 1as. The functional equation implies that I paragraph, S, has a simple zero at each even negative integer ZA equals AA2NA euro. These are known as the trivial zeros of I paragraph, S. For S an even positive integer, the product sin, I euro S/2, I, 1as, is regular, and the functional equation relates the values of the Riemann zeta function at odd negative integers and even positive integers. The functional equation was established by Riemann in his 1859 paper on the number of primes less than a given magnitude and used to construct the analytic continuation in the first place. An equivalent relationship had been conjectured by Euler over 100 years earlier, in 1749, for the Dirichlet eta function. Incidentally, this relation is interesting also because it actually exhibits I paragraph, S, as a Dirichlet series which is convergent in the larger half-plane I florin AA0, up to an elementary factor. Riemann also found a symmetric version of the functional equation, given by first defining. The functional equation is then given by. Riemann defined a similar but different function which he called a I3/4, t. Zeros, the critical line, and the Riemann hypothesis. The functional equation showed that the Riemann zeta function has zeros at a2, a4. These are called the trivial zeros. They are trivial in the sense that their existence is relatively easy to prove, for example, from sin, I euro S/2, being zero in the functional equation. The non-trivial zeros have captured far more attention because their distribution not only is far less understood but, more importantly, their study yields impressive results concerning prime numbers and related objects in number theory. It is known that any non-trivial zero lies in the open strips RA a car 0 a re, S, AA1, which is called the critical strip. The Riemann hypothesis, considered one of the greatest unsolved problems in mathematics, asserts that any non-trivial zero S is re, S, A equals A1/2. In the theory of the Riemann zeta function, the set ZA a car re, S, A equals 1/2 A is called the critical line. For the Riemann zeta function on the critical line, see Z function. The Hardy-Euro-Littlewood conjectures, in 1914, Godfrey Harold Hardy proved that has infinitely many zeros. Hardy and John Edensor-Littlewood formulated two conjectures on the density and distance between the zeros of on intervals of large positive real numbers. In the following, is the total number of real zeros and the total number of zeros of odd order of the function lying in the interval. For any, there exists a such that when and, the interval contains a zero of odd order. For any, there exists a and such that the inequality holds when and. These two conjectures opened up new directions in the investigation of the Riemann zeta function. Other results, the location of the Riemann zeta function zeros is of great importance in the theory of numbers. The prime number theorem is equivalent to the fact that there are no zeros of the zeta function on the re, S, A equals A1 line. A better result that follows from an effective form of Vinogradov's mean value theorem is that I paragraph, I florin plus it, a permel A0 whenever a tar A permel beta 3 and. The strongest result of this kind one can hope for is the truth of the Riemann hypothesis, which would have many profound consequences in the theory of numbers. it is known that there are infinitely many zeros on the critical line. Littlewood showed that if the sequence contains the imaginary parts of all zeros in the upper half-plane in ascending order, then the critical line theorem asserts that a positive percentage of the non-trivial zeros lies on the critical line. In the critical strip, the zero with smallest non-negative imaginary part is 1/2 plus I 14.13472514. Directly from the functional equation one sees that the non-trivial zeros are symmetric about the axis Re, S, A equals A 1/2. Furthermore, the fact that for all complex SA permil 1 implies that the zeros of the Riemann zeta function are symmetric about the real axis. Various properties, for sums involving the zeta function at integer and half-integer values, see rational zeta series. Reciprocal. The reciprocal of the zeta function may be expressed as a Dirichlet series over the Mach-paragraph bias function I1/4, n. For every complex number S with real part greater than 1. There are a number of similar relations involving various well-known multiplicative functions. These are given in the article on the Dirichlet series. The Riemann hypothesis is equivalent to the claim that this expression is valid when the real part of S is greater than 1/2. Universality. The critical strip of the Riemann zeta function has the remarkable property of universality. This zeta function universality states that there exists some location on the critical strip that approximates any holomorphic function arbitrarily well. Since holomorphic functions are very general, this property is quite remarkable. Estimates of the maximum of the modulus of the zeta function, let the functions and be defined by the equalities. Here is a sufficiently large positive number. Estimating the values and from below shows how large values can take on short intervals of the critical line or in small neighborhoods of points lying in the critical strip. The case was studied by Ramachandra. The case, where is a sufficiently large constant, is trivial. Karatsuba proved, in particular, that if the values and exceed certain sufficiently small constants, then the estimates hold, where are certain absolute constants. The argument of the Riemann zeta function. The function is called the argument of the Riemann zeta function. Here is the increment of an arbitrary continuous branch of along the broken line joining the points, and there are some theorems on properties of the function. Among those results are the mean value theorems for and its first integral on intervals of the real line, and also the theorem claiming that every interval for contains at least points where the function changes sign. Earlier similar results were obtained by Eitel-Selberg for the case. Representations, Dirichlet series, an extension of the area of convergence can be obtained by rearranging the original series. The series converges for, while converges even for. In this way, the area of convergence can be extended to for any Mellin transform. The Mellin transform of a function E, x, is defined as in the region where the integral is defined. There are various expressions for the zeta function as a Mellin transform. If the real part of S is greater than 1, we have where I denotes the gamma function. By modifying the contour, Riemann showed that for all S, where the contour C starts and ends at plus A and circles the origin once. We can also find expressions which relate to prime numbers and the prime number theorem. If I euro, x, is the prime counting function, then for values with Re, S, 1. A similar Mellin transform involves the Riemann prime counting function J, x, which counts prime powers Pn with a weight of 1/n, so that now we have. These expressions can be used to prove the prime number theorem by means of the inverse Mellin transform. Riemann's prime counting function is easier to work with, and I euro, x, can be recovered from it by Mach-paragraph bias inversion. Theta functions, the Riemann zeta function can be given formally by a divergent Mellin transform. In terms of Jacobi's theta function. However, this integral does not converge for any value of S and so needs to be regularized. This gives the following expression for the zeta function. Laurent series, the Riemann zeta function is meromorphic with a single pole of order 1 at ZA equals A1. It can therefore be expanded as a Laurent series about ZA equals A1. The series development then is. The constants I cubed n here are called the Schlotter's constants and can be defined by the limit. The constant term I cubed 0 is the Euler-Mascaroni constant. Integral, for all the integral relation holds true, which may be used for a numerical evaluation of the zeta function. Rising factorial, another series development using the rising factorial valid for the entire complex plane is. This can be used recursively to extend the Dirichlet series definition to all complex numbers. The Riemann zeta function also appears in a form similar to the Mellin transform in an integral over the Gauss-Kuzmina-Wiersing operator acting on Xr1. That context gives rise to a series expansion in terms of the falling factorial Hadamard product. On the basis of Weierstrass's factorization theorem, Hadamard gave the infinite product expansion, where the product is over the non-trivial zeros I of I paragraph and the letter I cubed again denotes the Euler-Mascaroni constant. A simpler infinite product expansion is. This form clearly displays the simple pole at Xr equals A1, the trivial zeros at A2, AA4, A. Due to the gamma function term in the denominator, and the non-trivial zeros at Xr equals AI logarithmic derivative on the critical strip. Where is the density of zeros of I paragraph on the critical strip 0A Re, S, AA1? Globally convergent series, a globally convergent series for the zeta function, valid for all complex numbers S except S equals 1 plus 2 I euro E A euro SHN log, 2, for some integer n, was conjectured by Konrad Knopp and proved by Helmut Hasse in 1930. The series only appeared in an appendix to Hasse's paper, and did not become generally known until it was rediscovered more than 60 years later. Hasse also proved the globally converging series. In the same publication, Peter Bowain has shown a very rapidly convergent series suitable for high-precision numerical calculations. The algorithm, making use of Chebyshev polynomials, is described in the article on the Dirichlet eta function. Series representation at positive integers via the primorial. Here Pn is the primorial sequence and Jk is Jordan's totient function. Applications: the zeta function occurs in applied statistics. Zeta function regularization is used as one possible means of regularization of divergent series and divergent integrals in quantum field theory. In one notable example, the Riemann zeta function shows up explicitly in the calculation of the Casimir effect. The zeta function is also useful for the analysis of dynamical systems. Infinite series: the zeta function evaluated at positive integers appears in infinite series representations of a number of constants. There are more formulas in the article harmonic number. In fact, the even and odd terms give the two sums AA and A. A where I cubed is Euler's constant. A where A represents the imaginary part of a complex number. Some zeta series evaluate to more complicated expressions. Generalizations: there are a number of related zeta functions that can be considered to be generalizations of the Riemann zeta function. These include the Hertz zeta function. The convergent series representation was given by Helmut Hasse in 1930, cf. Hertz zeta function, which coincides with the Riemann zeta function when q equals 1, the Dirichlet L functions and the Dedekind zeta function. For other related functions see the articles zeta function and L function. The polar logarithm is given by, which coincides with the Riemann zeta function when Xr equals A1. The Lurch transcendent is given by, which coincides with the Riemann zeta function when Xr equals A1 and Qa equals A1. The Clausen function CLS, I, that can be chosen as the real or imaginary part of Lee's, AE. The multiple zeta functions are defined by. One can analytically continue these functions to the n-dimensional complex space. The special values of these functions are called multiple zeta values by number theorists and have been connected to many different branches in mathematics and physics. See also, 1 plus 2 plus 3 plus 4 plus AA arithmetic zeta function, generalized Riemann hypothesis, prime zeta function, renormalization, Riemann-Euro-Siegel theta function, notes. References: Apostel, T.M., Zeta and related functions, Inulva, Frank W. J. Lozier, Daniel M. Burweisvert, Ronald F. Clark, Charles W., NIST Handbook of Mathematical Functions, Cambridge University Press, ISBN A978-0521192255, MRA 2723248. Jonathan Berwain, David M. Bradley, Richard Crandall. Computational Strategies for the Riemann zeta function. J-Comp. App. Math 121, 247 a €296. Bibcode, 2000 JCOM 121 247b doi, 10.1016 per second 0377-0427, 00336-8 a bibcode, A2000 JCOM 121 247b, Kvajovia, George. Kleinowski, Jake. Integral representations of the Riemann zeta function for odd integer arguments. J-Comp. App. Math 142, 435 a €439. Bibcode, 2002 JCOM 142 435c doi, 10.1016 per second 0377-0427, 02-00358-8. MRA 1906742 a bibcode, A2002 JCOM 142 435c, Kvajovia, George. Kleinowski, Jake. Continued fraction expansions for the Riemann zeta function and polylogarithms. Proc. Amma. Math. Soc 125, 2543 a €2550. doi, 10.1090 per second 0002-9939-97-04102-6 H. M. Edwards. Riemann zeta function. Academic Press. ISBN A0-486-41740-9 has an English translation of Riemann's paper. Hadamard, Jack. Sur la distribution des copyright de la fonction I paragraph, S, Aces consa copyright quinces arithma copyright X. Bulletin de la Société copyright Mathématique de France 14, 199 a €220 a, G. H. Hardy. Divergence Series. Clarendon Press, Oxford. Hass, Helmut. In Summierens Verfahren für 1/4 die Riemannsche Paragraph Re. Math. Z32, 458 a €464 doi, 10.1007/BF0119465. MRA 1545177 a, Aivic. The Riemann zeta function. John Wiley & Sons. ISBN A0-471-80634-X. Y. Motashi. Spectral Theory of the Riemann zeta function. Cambridge University Press. ISBN A0521445205 A. A. Karatsuba. S. M. Vronin. The Riemann zeta function. W. de Guiter, Berliner, Miesa, Istvan. Deal, Ian. Hypermonic series involving Hertz zeta function. Journal of Number Theory 130, 360 a €369 doi, 10.1016/JJNT. 2009.08.005. MRA 2564902 a, Hugh L. Montgomery. Robert C. Vaughan. Multiplicative Number Theory I. Classical Theory. Cambridge Tracts in Advanced Mathematics 97. Cambridge University Press. ISBN A0-521-84903-9 a Chapter 10. Donald J. Newman. Analytic Number Theory. GTM 177. Springer Verlag. ISBN A0-387-98308-2 a Chapter 6. Rao, Go. The distribution of the logarithmic derivative of the Riemann zeta function. Proceedings of the London Mathematical Society. S3 a €72, 1 euro 27 doi, 10.1112s3-72.1.1 Riemann, Bernhard. Aber die Anzahl der Primzahlen unter einer gegebenen Graph Paragraph SSE. Monatsbericht der Berliner Akademie A. In G. Sammeldwerke, Tubner, Leipzig, reprinted by Dover, New York. Sondau, Jonathan. Analytic continuation of Riemann's zeta function and values at negative integers via Euler's transformation of series. Proc. Amma. Math. Soc 120, 421 euro 424 doi, 10.1090 per second 0002-9939-1994-1172954-7 E.C. Titchmarsh. The Theory of the Riemann Zeta Function, 2nd Revised Edition. Oxford University Press, E. T. Whittaker and G. N. Watson. A Course in Modern Analysis, 4th edition, Cambridge University Press. Tsor, Jian Kayang. Analytic Continuation of Multiple Zeta Functions. Proc. Amma. Math. Soc 128, 1275 euro 1283. doi, 10.1090 per second 0002-9939-99-05398-8. MRA 1,670,846. External links, Haswinkel, Michiel, ed., Zeta Function, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Riemann Zeta Function, in Wolfram Mathworld Euro an explanation with a more mathematical approach, tables of selected zeros, prime numbers get hitched a general, non-technical description of the significance of the zeta function in relation to prime numbers. X-ray of the zeta function visually oriented investigation of where zeta is real or purely imaginary. Formulas and identities for the Riemann zeta function functions.wolfram.com, Riemann zeta function and other sums of reciprocal powers, section 23.2 of Abramowitz and Stegun, the Riemann hypothesis a visual exploration a visual exploration of the Riemann hypothesis and zeta function, Frenkel, Edward. $1 Million Math Problem. Brady Heron. Retrieved March 11, 2014 A.